In this video, we are going to learn how the data is exchanged between TCP entities. If we draw again, as usual, the TCP IP stack from host 1, starting from physical layer, link layer, network layer, transport layer, and application layer. First of all, if we are the sending host, we have to talk about the process that is involved between the applications and the transport layer. Then, if we also draw the TCP IP stack on the receiving side, we must talk about the process of sending information from the transport to the application layer on host 2. Then remember that in the middle there is the network, and we have buffers on the TCP entities for storing segments. So the communication between the application and TCP on the sending side is as follows. The application sends data to TCP when it wants, and if there is free space in the TCP buffer. Okay, so we have a buffer at the sending side. If there is space, the application is able to insert segments in the buffer to be sent. Then, when the segment arrives to the destination, there is another buffer called receiving buffer, where segments are temporarily stored, and the application reads from the buffer when and the amount of data it wants. There is an exception, urgent data, as we will see in the future. So, as you may know, TCP considers data as a continuous flow of bytes. Remember that we have the sequence field and the ACK field. So, in order to know how many segments have correctly arrived to the destination, which is the next segment to be sent, and so on. How is the protocol rules between TCP entities? So if we are at layer 4, host 1, host 2, transport, how is this dialogue? So the sending TCP entity sends data whenever it wants. Exception, post data. In this case, the segment must be sent as soon as possible. A very important parameter for a TCP connection is the maximum segment size. It means that if possible, we are going to send segments of this size, for example, 1 kilobyte. When this value is negotiated, so at the beginning of a TCP connection, during the connection establishment, the three-way handshake, in the first scene, the client will propose a maximum segment size to be used during the connection. So, for example, here we can say in the option field that the MSS is equal to 1 kilobyte. Okay, and the server in the second message of the three-way handshake will say, okay, I send you back the scene, the ACK, and I accept or not your proposal about the MSS. So again, if the option fields, the MSS is filled with the same value, I mean accepting the proposal from the client, or with a lower value, but not higher. when using the maximum segment size, we are trying to reduce the overhead. If we are sending data, segments with full size, we are reducing the number of segments to be sent. So the number of headers, information about control is reduced. So the number of segments as well as the information control is reduced. This is the concept of overhead. Let's see an example of data exchange between a couple of hosts. Host 1 on the left, host 2 on the right. We only refer to application and transport layers. So at first, the source application will push some data subject to buffer availability at the sending TCP. This is the sending buffer. If there is space, the source application can send something to be sent to the host 2. Then when we are a transport layer, we can send TCP segments to the receiving TCP entity according to the free space in the receiving buffer. If you have space, I can send you TCP segments. And also we have to consider the congestion in the network. Okay. Then when the segments are received from by the TCP entity, the application can read some portion of this buffer according to its criterion. If there is data to read, for example, imagine this is a buffer of 4 kilobytes, and there are a couple of kilobytes already stored in the buffer. The application can say, okay, I can read 1 kilobyte, couple of kilobytes, and then they are free from the buffer. The same example, but with realistic data. For example, the source application wants to send 4 kilobytes to the destination application, and at the end, the source application writes 4 kilobytes that are stored in the sending buffer. The sending TCP entity knows which is the free space in the receiving buffer from the receiving TCP entity. So it can read different number of segments according to the maximum segment size. For example, in this case, if we are sending 4 kilobytes, at the end we have to send 4 different segments with 1 kilobyte each. The maximum segment size is 1 kilobyte. Then imagine that the buffer again is 4 kilobytes and it is full. After receiving the 4 segments, the application can read, for example, first a couple of kilobytes, 1 and 2, then 1 kilobyte, then another kilobyte. When and how much information it wants about the application. So at the end, the MSS is not negotiated. It is imposed by the client. If the client wants, for example, MSS of 1 kilobyte and he's saying, okay, this is my proposal, the server can say, no, I cannot accept 1 kilobyte. Let's reduce it, but never increase it. This negotiation is though by means of the option field of the TCP header. It's not a field. It's inside the options in the first and the second segments of the three-way handshake. Okay, and this segment size is referred to date. Don't take into account any header. So default values, for example, 536 bytes for an IP datagram of 40 bytes more, 576 bytes. This could be a default example value for the MSS. There are special cases for data exchange between TCP entities. The first one is the push date. Remember that there are 8 flags or bits in the TCP header. One of them is PSH, push data. So when we add this bit, we set this PSH bit active, the application asks TCP to send data as soon as possible. We are not waiting for filling the maximum segment size. So if there is only 1 byte, for example, with PSH active, we are sending the segment as soon as possible. And the receiving TCP entity will put them at the disposal of the application. And the application will decide when and how much to read. For example, application telnet. This bit doesn't modify the processing order of data. Situation, which is done by the urgent bit flag and the urgent offset. In this case, there can be a bypass of data. So data are delivered to the remote application without waiting. So we can imagine a kind of priority for this type of segments. Example, pressing Ctrl+C in a telnet session. We are aborting the process by passing data that are not priority. In TCP, we can find 2 different types of traffic. Interactive traffic, generated by application that sends data in small quantities, for example, telnet for remote login. And the other option is to use massive traffic. Massive traffic is referred to maximum segment size. A difference is between interactive and massive. It's that for interactive, we have very small segment, but for massive, we have segments of full size. For example, many applications like FTP, SMTP, HTTP, and so on. Let's start with interactive traffic, and in particular with the protocol telnet. Telnet is the acronym of Teletype Network. It's an application layer protocol used for emulation to be remotely on another computer. So the idea is to press a key and send a segment to the destination, and the destination will send the same key back to me, and then I can impress it on the screen. So it's called remote echo. For each key that is pressed, at least 2 packets are sent. One to go from the client to the server, and then one to go from the server to the client. But normally, 3 or 4 packets are sent for each key that is pressed. Let's see a couple of examples between a telnet server and a user, telnet user or client, that are quick, slow, and also the quick, slow telnet server. At first, we start with a slow telnet server. We have the client on the left, the server on the right. Imagine that we are on the second stage of the TCP connection, data transfer. The client types letter C. One segment is sent only with this information, letter C, with a particular sequence number and a particular ACK number. The server has to send an answer with the same data to the client. But since it is a slow server, it cannot process the application in a very fast way. So he has to wait a little bit, but at the end, he has to send an ACK, because otherwise the timeout here will expire and a retransmission of the same segment is required. So in order to avoid it, the server will wait for a specific period of time, for example, 200 milliseconds, and then send an ACK that is empty, only for acknowledging the sequence number 92. Sequence number 109, because It's the one that is asked from the client, ACK93, because I have received 92 plus 1 because data is 1 byte. And then after processing the segment, now the application has been talking with the transport entity, and it is able to send the data back. So same sequence number, same ACK as in this case, but the difference is that here we have include data. And then the client waits for new potential data. Imagine that we don't press any other key, and then he has to send an ACK back, because otherwise the same process. Here we have a timeout, and there will be a retransmission. So the TCP on the client sends an ACK of the received segment, an empty ACK with sequence number 93, the one that is required from the server, ACK 110, because I have received this sequence number plus 1 with data. So this is the ACK. So at the end, for one key that is pressed, C, 4 segments are transmitted because it's a slow server. So we have to introduce the concept of delayed ACK timer. This is the time we have waiting for new data to be included in the ACK. So the idea is to not, if we receive a segment with data, the idea is to not answer very fast with an empty ACK. Since we have to send an ACK for acknowledging the previous segment, we are going to introduce data if possible. So we are waiting a little bit and then introduce the data. If we don't have data to send, obviously we have to send the ACK. This is the process that we have been following with the server. So this technique is called piggybacking. So the ACK is appended to data when possible. Okay, piggybacking technique. Which is the time to wait, more or less 200 milliseconds. However, if the time expires and there is no data to send, a segment without data is sent only with the ACK flag active. Let's have a look again at the previous example. The client sends a segment with letter C inside, only 1 byte. This is 1 byte. The server is waiting for potential data to be included. Remember that we have to include data C as well. But the timer expires. So the server must send an empty ACK. Once the server has processed the segment that it has received and the application is able to send back the data, it will send back the same character and the process finishes. The client waits again the 200 milliseconds because in this case the client is not sending any type of data. And then we have 4 messages for only 1 character, that is C. Then let's look at the example, the same example, but with a quick server. In this case, same situation, user types C. The server start the ACK delayed timer, but before expiring, we answer with the same data. So in this case, we have 3 messages for 1 key that is pressed. So this is the difference between a slow server and a quick server. 4 and 3 segments transmitted per character pressed. It is obvious that if we have to wait a little bit before sending an empty ACK, if we have data, we are going to exploit this piggybacking concept to improve the TCP performance. But even so, it's very low efficient for interactive flow. Interactive traffic is, for example, telnet traffic, in which we are sending data without full size. So the Nagel algorithm is based on a new idea that if we have to send data in small segments, let's wait a little bit for the ACK referring to the previous segments. In this way, we are waiting for increasing the size of the segment. So it is an auto-adaptive mechanism, but there can be problems. If the network is more loaded, the ACKs will be received later and the segments will be bigger. So the idea at the end is to send segments of big size, approaching to the massive traffic to the maximum segment size. And the Nagel algorithm acts on the sending TCP entity, not on the receiving one. But we can have the so-called silly window syndrome. Imagine that the client is sending data to the server very fast, and the server has the receiving buffer full. All the slots are stored by a segment. So imagine that the server is able to free space to read. The application is able to read very, very slow. So here we have 1 kilobyte free, and B is able to notify that the window is only 1 byte or 1 kilobyte. So A will send very fast again a new segment. Then the buffer is again full. But the server is able only to read 1 byte each time. Again, window 1 byte, A will send a new byte, and the server will also again be filled. So starting from point 3, buffer full, the receiving TCP entity will notify that the buffer is full, window is 0. The receiving application can read only 1 byte per iteration, let's say, and then notify TCP entity it has 1 byte free. The window is 1 byte. Then the sender will send 1 byte. The buffer is full, and this process is repeated every time. So in order to solve the silly window syndrome, let's see an example. Starting from the buffer full, the application reads only 1 byte. So we have only 1 byte in the buffer free. But we have to notify the sending side with a segment, and this segment will have the IP header, the TCP header, for saying, okay, the window size is only 1 byte. So imagine we need 40 bytes for saying this simple thing, window equal to 1 byte. So the overhead is increasing. So after receiving this segment from the client will send 1 byte again. Then window size equal to 0, and so on and so forth. How to solve this problem? By means of the Clark solution that is defined in the RFC 813. This is a solution to the silly window syndrome, and the idea is to, the server or the receiving side will notify the sending only if the window size is or 1 MSS or the half of the buffer size. For example, if the buffer at B is 4 kilobytes and there are only 2 kilobytes that are stored inside the buffer, we can notify A. Or if we have agreed that this is only the the MSS is 1 kilobyte, we can also notify A. Okay, these are the two options. We need to have at least one MSS free in the buffer or the half of the buffer size. Once we have finished with the interactive traffic, we move to massive traffic generated by applications that transmit data in large quantities. Examples of applications: FTP, SMTP, or other types of protocols like the web, HTTP. The important key thing here is the MSS. So the segments will be of full size, MSS. But obviously we have a higher efficiency if we send a less number of segments compared with the interactive traffic, in which maybe only 1 byte is sent. We can have two main problems. The first one is related to the receiver. If the receiving buffer is full, so there is a mechanism to say to the sender which is the size of the free buffer we have. And this mechanism is called TCP flow control. The other problem is maybe not related to the destination, to the receiving TCP entity, but inside the network. The network can be congested. The buffer of intermediate system routers maybe is full. They are full, so there are no space. So in this case, the packet will be lost. So the other mechanism that is used by TCP for massive traffic in order to maximize the efficiency is the mechanism called congestion control.